this video, probably in the second clip we're in now, we're going to be looking at these sort of materials along here, and you can see a massive range of different types of materials. Jake's going to be cutting a golf ball, melting some metal, blowing up some inner tube tyres to show some examples, melting an ice cube with fire, making custard to show you what custard the material is actually related to. He's also going to be making fire from the sun, apparently. He's going to be changing the colour of plastic using UV light from the sun. But on the table here, Shed Hackers, you can see some of the sort of materials we're going to discuss in this next clip. And they're not as obvious in terms of their properties as you might imagine. Jake, how's the golf ball cutting?
Yeah, it seems to be going all right. Oh, look.
Oh, that's it. Okay, well, let's have a look at it.
Well, it's in two pieces now.
Let's have a look. Oh, do you know, years ago they used to be full of rubber bands all sort of combined together, rolled together. And that is just a pure polymer by the looks of things. Well, there you go, Shed Hackers. That is well, it was a golf ball. Just turn it, yeah, that definitely was now. Well done, Jake. Was that hard work?
Yeah, it was actually.
Yeah, that has to take a lot of force, a lot of impact force, doesn't it?
And some of the really new ones, or the expensive ones, they have a soft core and a harder outer shell.
Oh, right, so they can take perhaps even more impact.
Yeah.
Go further. Brilliant, that, Jake, well done.
Is that a wooden lock?
Yes, it is. And it shows actually the wooden key and how it interlocks with the mechanism inside. And there's a more advanced one made from brass.
So will that be from hundreds or thousands of years ago?
Well, it says 2,000 years before Christ. So the Egyptians, it says, made wooden locks. How impressive. And these aqueducts here that hold water, all made from stone, but stone very carefully chosen. And on this page it talks about how stone masonry was developed over years to make bridges, and how carpenters made things very finely from obviously using fine-edged steel and iron tools.
Wasn't Jesus a carpenter?
Jesus certainly was a carpenter, yes, and it makes quite a few references to that in the Bible. But even the use of fabric and how fabric's changed over the years. I mean, even have to look at the last 50 years, and fabric has really become quite an impressive piece of technology in itself. It's self-illuminating, those that can insulate from heat, those that actually, in a sense, keep you very, very warm. All things that 100 years ago were virtually impossible. Here's another interesting clip. Look at the old gramophone here, look. Look at that old record player. Look.
Wow.
Mechanical, a wind-up one, and it amplified the signal from a little needle or stylus into the cone, which amplifies the sound. And yeah, moving on a little bit, look at this motor car, developed by Carl Benz back in 1885. Look at the old materials used, incredible. And of course, all these old technologies and old use of materials develop over the years into newer use of materials. And they become more refined and more useful, I suppose, in that sense. What do you think that is, Jake?
Maybe some sort of speaker?
No, look, it's a television from the 1920s. Look how massive. That's probably as big as you are tall.
Wow.
I know. And it used a cathode ray tube. Different technology used then and different materials used then to make the devices. But yeah, it just shows how things have moved forward, haven't they? I mean, that would weigh probably about 35 to 40 kilos, if not more. Okay, so I wanted to talk about this chap here, and this chap is Sir Frank Whittle. What do you think he developed?
The jet engine?
He did, and that's an enormous jet engine there he's standing next to. There he is, and I've actually met Frank Whittle in a museum.
Is that a helicopter?
Yes, we looked at that earlier, again from the 1920s. John Burnell, incredible piece of equipment. Again, very dangerous flights were made in order to test out materials, but here's an example. I mean, look how crude that looks. And there he is sitting there ready for it to take flight.
What's that? So
That's an image of a very, very, very small bug or insect. And it's an insect that's found, or creature, in human clothing and perhaps even human beds. And that's been picked up by a device called an electron microscope. And that can see items down to 10 to the minus 9 and smaller. And it uses certain electron waves to detect the image, and then it converts them. Very clever.
Wow, Dad, that's impressive.
Do you know what aircraft that is?
No, but I know it looks quite powerful.
That is a Mark I Spitfire. Amazing piece of engineering at the time. And it helped enormously in the Great War. And interestingly, this book's all about it actually. I've got some other images. I think there's one of the engine. Oh, there's the anatomy, they call it, of the aircraft. It shows all the various components, componentry, and the actual aeronautics, the airframe as well. How it's all put together. Amazing, isn't it? And then here it shows, look, it being fabricated, made together. And they actually did use fabric on some of these aircraft. They're not just metals.
But wouldn't the fabric burn under the intense heat?
No, it's treated. A lot of it was treated very carefully for chemicals. All part of this whole topic, really, this clip. Some of the materials they used were designed specifically to resist heat. Look at this engine.
Oh,
A Merlin engine it was. A V12. Massive engine. And on this page you can see the Harrier jump jet. I mean, we take a lot of the aircraft we fly in for granted, but they've come a long way in just 50 to 100 years, haven't they?
Mm-hmm.
And so has electronics. We're going to talk about electronic components a bit later in one of the clips, and how they've helped us in all sorts of ways, medical science in particular. Look at this aircraft, the stealth aircraft.
Wow.
Yeah, amazing.
It looks very flat.
F-17A. Goes at over 2,000 miles an hour, that.
Wow.
Ah, yeah. Genetic control. He's talked about genetic control and engineering. Very impressive. And one thing I did find out, this, look. This is interesting. This is at a microscopic level. That means you can't see it at all. This is the outer coating made from 4 different proteins. And they're man-made. It's a synthetic virus they've made here to counteract polio. That means to stop polio happening.
So would they make a virus to stop another virus?
They can do. And of course we're in a situation at the moment where there's viruses we really don't know enough about to stop it becoming very, very dangerous to the world.
Mm.
Go back to that though later perhaps. Oh, there's this clip here on the Mars rover. Now that's full of very, very advanced materials. And the material science in that is something perhaps we'll touch on a bit later, but the resistance to wear and corrosion and temperature and chemicals in some of the materials used there will be very, very impressive. Okay, we'll leave it there for a moment.
When you talk about properties of materials, what do you mean?
It's a good question, and I think a lot of people do find this subject quite difficult. I've printed off these worksheets and I've tried to write down what I've found from the various information and the research I've done. And here is a sort of a group of words I've tried to collect together to show the most common terms used. And these are called working properties, and some people call them mechanical properties. And what it basically means is how materials react to an external force or condition. I suppose in some ways to the environment they're in. And that's really critical about the design and use of certain materials. Compression is a really interesting topic. Can you think of one piece of material that you know of that's really good in compression? It can take a lot of compression.
Concrete?
Concrete, and it's used extensively in house foundations and all sorts of structures, bridge structures. It's because it can take enormous amounts of crushing forces. Moving on a little bit, the durability is a general term, and its resistance against wear over time.
So what's ductility?
Ductility is the ability to be stretched and drawn under tension, when the thickness can still be allowed to reduce, but it doesn't break. It's a really hard one to explain, but at aluminium you can actually stretch it and it will become thinner, but it won't break until it gets to a certain point called its yield point. But perhaps we'll touch on that a bit later. Okay, and then elasticity, that's a little bit more easy to explain. Of course, an elastic band is an example of elasticity, and anything which has the ability to stretch is known to be elastic in some way, and it's connected with another word called plastic. And plastic is another term used in connection with elasticity. Okay, so that's the ability to stretch without permanently change in its shape. So there you go. Hardness. Well, hardness. Can you explain hardness, Jake?
Would it be ability to resist scratching?
Yeah, so if you try to scratch some metals and glass, they're so tough and resilient, they don't scratch very easily. And that's a sign of hardness. And the test for hardness often uses a very hard material such as a diamond, and they actually score it and see how easily it scratches or indents. Okay, that's hardness. Malleability, ability to withstand deformation or deformation by compression without cracking. Okay, so another hard one to explain, and perhaps we'll touch on that a little bit later, and that's malleability. Strength, a general point, okay, of resistance to all sorts of forces, a little bit connected to toughness. So strength is a general term, okay. Shear, well, that's the ability to resist cutting. So paper is very poor in shear because you can cut it very easily, but you can't cut metal very easily, and you can't cut diamonds very easily. Shear is the ability for it to be easily cut. Stability, that really relates to the product or the material not changing from one state to another in a given temperature. So some materials actually are very unstable, and they can suddenly change to a liquid or a gas, even with a couple of degrees change in temperature. Okay, we'll leave it there and come back.
Please don't attempt anything we do in this video at home.
Hi guys, and in today's clip we're going to be breaking some materials to test them for toughness and impact strength. So that was the end of the test, and we're going to take you through all the items we broke, and we're going to break one final product, not just one material. And what do you think that's going to be, Jake?
My phone!
No, not your phone. It's an iPhone.
So what's toughness?
Toughness, there's the spelling. It's the ability to absorb impact. So I suppose a tennis ball can do that. It can take impact time and time again, and it won't break or crack.
So what about spring?
A spring, yes, to a point. I'll give you an example of a spring. Now here's a spring. It is tough, but it's not a really good example. But if you stretch it, it will return back to its original shape. But if you stretch it to a certain point, the elastic limit, if you like, it's called, it then stays, as you see, the same shape as you've pulled it apart from. Okay, so I think a good example of toughness really is maybe something like this, really resilient to wear, both the tyre and the actual wheel hub. Very tough and strong. And a bolt, I suppose, is tough and strong and can take a lot of force from all sorts of angles, pulling and crushing force, and torsional force, twisting force as well. That's a good example. Does that help?
Yeah.
So torsion, that's actually a good one, because it moves on to torsion. Torsion is the ability of a product to be able to be twisted without it actually damaging. And steel is a good example. You can tighten a nut on this, tighten it very, very tightly, and it really won't try and twist itself, unless obviously you overload it. But they can take, hundreds of tons of force in twisting motion, some of these large nuts and bolts. Okay, and they're often used in car suspension as a way of supporting the car. It's a certain type of method they use, called a torsion bar. And lastly, tension. That's resistance to being pulled or stretched without permanent damage. I think that's an easy one to demonstrate. So the demonstration would be a piece of string, and you see these on very large boats, don't you? Nylon cord, and even you see, just stay there a minute. You see metal, don't you? Metal wire used on bicycles. But on a crane, you'll see one which is literally that wide, solid, almost solid metal, but it'll be woven together into a steel cable, and they can take enormous amounts of tension. Can you think of anything else that takes tension?
I'm not quite sure.
What about a cord from a fishing rod or a strimmer?
Oh,
I can take it.
yeah.
Lots of pulling force. I couldn't break that. You could probably pull a car along with that thin cord. Yeah, amazing. Okay, we'll leave it there then.
So, what you do?
Ah, hi Jake. Well, actually, I'm going to do some destructive testing on some materials, just to excite things up a little bit for our viewers. And I thought we'd start on looking at brittleness, durability, strength, which is the general ability to resist all forces, a little bit on stability, I suppose, in some way, but certainly toughness. That's going to be our key area for the next few clips. And I hope, Shed Hackers, you stay with us and enjoy this. Jake's going to be breaking a few items.
Yay!
First, glasses on. Collect hammer. Oh, hammer's a feather. Oh, as expected. Two. The potato.
Yeah!
The bottle. Oh, oh dear. The house tile.
Ooh.
Broken. Oh, it's broken.
Too.
Oh, that broke easily. Cardboard box. Oh, it's quite hard. Quite tough.
Oh,
Ah. Can't really crack that one, can you? The glass mirror. Oh,
wow.
The ceramic plate. Aluminium nail. And again. Benzies. Now the light bulb. Oh, now the polypropylene pig. Now the steel can. Now the lead pellets. Now the polymerized rubber.
Oh!
Ah, very resistant. And again. Yeah, well done, rubber. Now the polyethylene propeller blade. Oh,
whoa!
It cracked. I'm surprised. Now the piece of pine wood. Tough. Yep, and again. The wood is tough and bead. Ah, in small quantities it's much weaker. Handle grip we think is a polybutylene or some type of silicon rubber. We're not sure.
Maybe.
Off you go, Jake. So that's very tough and resilient. Well done. This is a house brick made from clay. Oh, very brittle. Could take a lot of compression, but not a impact force. Markings there, Jake. What is this?
Polyethylene.
Polyethylene, so it's a type of plastic. So, destruct. Tough. Very, very tough. How thin it is as well. Keep going. And that's taking a lot of impact force. Keeps on bumpers on cars. What's this one?
Polyvinyl chloride?
Polyvinyl chloride. And what is it? It's a piece of rainwater pipe.
Yes.
Okay, you may have to hold one end to crush it. Or, yeah, don't know. Yeah. Hold one end, that's it. Oh, it's going to fly off. And hit the end here. Hard as you can. Right. That's enough. That's extreme. That's very, very, very tough and resilient. And what was that? PVC?
Yeah.
Well done. So, what's that?
Mini iron magnets.
Mini iron magnets. Okay, off with the iron then.
Wow.
Oh.
Oh.
Oh. So, yes, that's very... What would you say? What's the term?
Ferrous, maybe? Or magnetic?
Of course, it's brittle. Brittle fracture there all over. See that, guys? Okay. Okay, Jake. And what's that?
A glass marble.
A glass marble. Okay, marvellous.
Oh my god, that's a lot stronger than I thought.
Oh, okay, do the blue one. Do you know, I thought that would shatter.
It's pretty strong.
And again, oh, it's gone.
Wow.
It's exploded.
It's just
This is a weight from, obviously, some little dumbbells. 1 kilogram, and it's made from
iron.
cast iron. That's it. Off you go, Iron Man. Cool. Oh. Oh. Oh my god, blimey.
Gosh.
We've done a destruction test. What do you think that is?
Leather.
Turn it over to show the viewers. Yeah, it's dyed or tanned leather. Very, very impressive stuff, leather. Obviously from an animal. Right, which animal? Probably a cow.
Yeah,
or
maybe
bull.
a cow.
Yeah, hopefully nothing else. Right, okay then. Sorry about the wind out here, guys. He's broken the test slab, so see what we can do with the leather.
Yeah.
Go for it.
Oh.
Well, that is tough. And still very flexible, of course.
Look at that.
Try and break it, try and rip it, try and tear it. Jay, where have your muscles gone?
Look, there's a tiny hole in it.
No, I think you're making excuses. A polyethylene or polypropylene. I think it's a polyethylene though. And it has two types of plastic, so perhaps the hub is polyethylene, polypropylene on the outside. Or maybe an elastomer. Off you go, Jake. Smash it out. Harder, 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 harder. Blimey, that's taking a hell of a whack. No, that's not, that's tough. Ah, poor little G. Oh, no, better do the bolt first, okay?
Yeah.
Go for it. Oh dear.
Oh gosh, we've broken the bed.
Right,
Let's give it a couple
go.
more.
Oh, you bent it at least. Okay, show the viewers, let's have a look. Okay, you've dented it slightly, but
And bent it a little.
you've really encouraged it with a hole in the slab, of course, to bend it.
Yeah.
That was putting on a lot of hammer. Do another big hammer job. Yeah. Right, that's gone. But you know, it's still very, very tough. And look how thin it is, really. So very tough. Steel, that is.
Yeah.
Steel bar. I think it's electroplated to stop it rusting. Oh look, there's a reinforcement in the slab I can see sticking out.
Oh yeah.
Oh, there you go.
It's just
Keeps the concrete in tension. Right, ball race in a ball race. So in a bar, I don't want this to flip in my face. So carefully, Jake, on this one. Yeah.
Oh my
Don't
god.
hold the end. I think hold the end, and yeah, I don't think you're going to be able to break it. Maybe you might crack. It's quite a brittle metal lead. You. Oh yes. Keep going. Keep going. Oh, you've broken the concrete now. Keep going. Keep going. Right. Let's just stop there. Let's have a look. Is it broken?
Yeah.
It has cracked. So it's quite a. So that's a brittle metal. It's brittle steel. Okay, it'll be some sort of tool type steel, but it's high carbon steel. But the bearings are still in place there.
Yeah,
isn't it?
and look, it still runs actually
That's
quite
amazing.
smoothly.
Is it really?
Yeah, it runs quite
That's
smoothly.
absolutely amazing. Well done, Jay. Jay, what do you think of this destructive testing we're doing today?
Well, it's very fun.
And what are we doing lastly?
The ball bearing, which
Now there's the ball bearing, guys. And we know they were ball bearings inside there somewhere. If I can get it.
I think you're
Cage is
going
slightly
to.
snapped, but right, looks like an explosion's happened here.
Yeah.
Right, let's go for the ball bearing. I have to move the camera
Okay.
back a little bit, but
Yeah.
go.
Oh.
Put it back on. That's it. Another one.
Oh
Oh dear.
gosh, this isn't good.
No. Right. Can you see the hole it's left in the slab? Give it another bash. See if you can get it. Right. Okay, that is the toughest of the lot.
Well, we
Ball
think so.
bearing, and it'll be made from a high carbon steel. And yeah, that's so we've had a bit of fun today. What do you think you've learned from today's test?
That in this test with the impact, the steel is the strongest because it's got a high enough carbon content to make it hard wearing, tough, but it's not too high where it will just shatter.
Great, and of course the other materials we discovered, although they can't take impact, they're all designed for specific purposes. So they have their own qualities, and that's why the material properties, each of those materials, is so important. Well, I hope you enjoyed that little clip there, guys. Catch you in a minute.